So let's begin the class today. So it's lecture 18. So, we were doing some concrete examples of stored energy function. So we'll continue with that. Let's say popular examples. That is W. Okay, so the first one that we talked yesterday was Saint Vennat-Kirchhoff isotropic material model. Okay, so according to this, the stored energy function or strain energy function W, which depends on F, or you can say it depends on the Green Lagrange strain tensor E, right? That comes due to objectivity. So this is equal to lambda over 2 times trace of this Green Lagrange strain tensor E and then whole square plus mu times E double contraction E. Okay, so that's one of the models, and here it has got just two parameters. So you can see it's a quadratic model. It's quadratic in strain, isn't it? It's quadratic, unlike the one that we derived in the last class, where it was the function of invariant, some arbitrary function of invariance, and we said that it has infinite constants. But this is a quadratic model. Quadratic isotropic model.
Sir, this expression, are we encountering it for the first time or are we getting it from some of our previous discussions?
No, we are encountering for the first time, and actually, if we have also given you the assignment, no, the last assignment,
S with respect to
where
T.
you had to derive the linear relationship between second pk and strain. So this energy model will lead to that particular linear relationship.
Okay, sir.
Yeah, two constants lambda and mu, which are also called Lame's constants. So this is not derived from anywhere. This is, just some proposition. And this is the most general form of quadratic isotropic energy. Okay. And so from here, when you derive the second pk, which is S, that's equal to del phi hat over del capital E. When you work it out, it comes out to be lambda times trace of E into identity plus 2 mu into E. Or in index form, it is Sij equal to lambda times EKK delta Ij plus 2 mu Eij. So this relationship is something which should come out from your assignment. This is the answer. It will come out from the last assignment of, or last problem of assignment 3.
Hello, sir.
Yes.
Sir, here this just the expression which you have written. for the energy model,
Yeah.
can't we say that it is derived by integrating the expression of the second Piola-Kirchhoff phase tensor for linear elasticity?
Integrating. What do you integrate?
Like it is as we can write as del psi by del E, and
Yeah.
then we can integrate the expression of S to get. Then we can integrate this expression to get psi in terms of E.
I see. I see. And the one from linear elasticity you are saying.
Yes, sir.
Well, so in linear elasticity, so okay, that's a nice point. So in linear elasticity, we say that for linear isotropic model, sigma ij is equal to lambda times epsilon kk into delta ij plus 2 mu epsilon ij, where epsilon is the infinitesimal strain tensor, which is this one. Now, of course, this relationship also comes from imposing the isotropy constant, isotropy assumption. The most general form is sigma ij equal toCijkl into epsilon kl, where this is a fourth order tensor. But the fact that sigma ij is symmetric and epsilon is also symmetric, and then further imposing the constraint of isotropy, theCijkl turns out to be such that it yields this particular relationship between sigma and epsilon. Okay, and of course, so this the energy model that we have here is actually in a way extension of this energy model in the linear elasticity to non-linear elasticity. All that we have done is simply replaced the infinitesimal strain tensor with the full Lagrangian strain tensor. So, from here, when you work out your W, so W is half sigma ij into epsilon ij. Okay. So when you work it out, it will come out to be lambda by 2 epsilon kk into epsilon kk, or I should say epsilon jj, or so it's just trace of epsilon, no? So trace of epsilon whole square plus mu times epsilon double contraction epsilon. Okay, and you can see that, so this is in linear elasticity, and we have simply extended it to non-linear elasticity by replacing this epsilon tensor with the green Lagrange strain tensor here. So that's the extension to non-linear elasticity. So in a way, it is just taking into account geometric non-linearity, because we have replaced the small strain tensor with the full green Lagrange strain tensor, but it is still materially linear. Okay, and when you work out the first derivative from here, it turns out on the left hand side you get second pk instead of Cauchy stress sigma. In linear elasticity we get second pk here. Okay, I hope this is clear to all of you. And so from And as I was telling you last time, once you have second pK, you can also get the expression of sigma. So sigma is simply 1 over det F into F into S into F transpose, isn't it? So that's going to be 1 over det F into trace of E into FF transpose plus 2 mu into F into E into F transpose. Okay, and when you replace E by half of F transpose F minus identity, then it becomes 1 over det F into trace of E, and you see FF transpose is B, isn't it? Left Cauchy green tensor, plus mu into, and when you put this, you get B square, mu into B square, and there's one more, minus mu into B. Okay, so this is what you get for sigma. Yeah, say again, I could not hear you. Hello?
Sir,
Yeah.
for example, like this Cauchy stress was a stress tensor in deformed configuration, while the first pK was the stress in undeformed configuration or reference configuration. What does second pK and biotensor physically signifies? Answer the second question is, why do we need this much different measures of stresses?
Yeah, that's a good question. See, first of all, sigma certainly is the stress tensor in the current configuration. That is the actual, we also say it to be the true stress. So if you cut the deformed body, then the traction that you feel in the cut section will be sigma times the deformed normal n. So that's the true stress that you will measure. Okay, but so what is then big P? So that's a very good question. So what is the physical meaning of big P? So it is wrong to say that first pK is the stress tensor in the undeformed configuration. As you see the sentence, you are saying in the undeformed configuration. But in the undeformed configuration, if it's a stress-free configuration, there is no stress.
Sir,
So first, yes,
Cauchy stress tensor corresponding to reference configuration.
yeah, right, that you can say. But we can say something more. So you remember how we derived this formula for first pK? We wanted to write down the traction in the deformed body in terms of original configuration, isn't it? So we said that the traction, or maybe let me do this again. So here is the reference configuration deforming to current configuration, and think of a section here with normal small n, and that section would be, let's say, something like this here, having normal small m, or maybe big N, big N,
So can we what is the stress that we would need to go back from deformed to deformed configuration, the first PK?
See, it is just that first PK is, we are trying to, let me complete it, okay? Then maybe we can discuss it.
Yes, sir.
So when we talk of what is the total force on this section, let's say here in the deformed configuration, we have this section. So total force on this section, suppose it is omega, then F omega. So, when you cut the section, one part of the body is going to apply force on the other part of the body, isn't it? So let us say I take the left part of the body. So I have this left part of the deformed body. Having outward normal, whose cut section has the outward normal N. So on this left part, right part of the body is applying traction. And totally, and as a whole, it is applying this force F omega. So this is the force from right part on left part. Okay, and this would be then integration over the section omega, and you have sigma multiplied with n d omega. Okay, the same section in the reference configuration is omega naught. Now all that I want to do is I want to write down the same force F omega in a Lagrangian framework. So see, right now it's an Eulerian framework because your domain is a small omega which is changing with time. Can I convert this integral into an integration over the reference section? So when you want to do that, then you have omega naught and you have sigma and then n d omega. So this is n d small s. So you know how area transforms, area vectors. So that is simply, I guess, you have a det F into F inverse transpose into big M into d omega naught. So this whole thing is for n d omega. And then we write it as omega naught 1 over det F sigma F inverse transpose into big N d omega naught. Okay, so this is here big N. And this thing is called first PK, big P. So it's just, you can see it's right now it looks like it's a mathematical quantity. I just want to work out the total force in a Lagrangian framework. And then when we did the transformation, that the thing inside the bracket, I'm just calling first PK. Okay, but it has some physical meaning also. For example, you see, so what we have said is that sigma into small n into d omega, that's equal to big P into big N into d omega naught. Okay, so basically, if I think of a very small area over here, so over that area, you have a force d big F acting there, D big F. So this is that force D big F. Now since this area has got small area is on a section with normal small n, so the traction is sigma into small n, and then I multiply with that magnitude of that area d omega. And then that same thing in the Lagrangian, it is P into big N into d omega naught. So that area must be somewhere here. Okay. So from here you see sigma n is equal to d capital F by d omega, which is also called small t, the Cauchy traction. And as per the definition, this is force per unit deformed area. So this is whatever is a force acting per unit deformed area. Whereas if you look at this relationship, then what you get is P into big N is the same small force big F, but you divide by d omega naught. So that we call big T. So this is also called referential traction, which is force per unit undeformed area. So that's the simple meaning. Okay. For example, think of, suppose you have a beam which is clamped at one end. So it is clamped here. And then you are applying a force, let's say big F, at the other end, a constant force F. Now, if that force is uniformly distributed over this area, so if it is uniformly distributed, over the end cross section, well, I said let us suppose it is uniformly distributed. So in that case, what will be small t? Small t will be that force F divided by the current area of the cross section, isn't it? Let us say small a. But the current area of the cross section is an unknown. We don't know how much is the current area. So this is unknown. Whereas big T, which is force per unit reference area, isn't it? So that's big F by reference area, let us say big A. So that is known. Okay. In this particular example, it is big T which is prescribed by the user in case F is constant. I'm saying it is constant. Or in other way, what you are prescribing is big P into the normal. Let us say it is E3. So big P E3 is prescribed by the user. Although you see it's sort of mathematical quantity, but knowingly or unknowingly, it is big PE3 that is being prescribed. Whereas sigma into n, which we don't know what it will be. See, the normal n is also going to change as the beam deforms. So this is sigma into n is unknown here. And that's because your force by area, the deformed area, is not known. So you are not prescribing sigma n, although it looks like a true stress, but this is not something that you are prescribing here. Okay, so you see the meaning of now first pk and the Cauchy stress. I hope that it clarifies. Now there are other stress measures also, second pk or the Biot stress. Well, they are sort of more like mathematical quantities. Also this big P is like a mixed stress tensor. Why it is mixed stress tensor? Because big P, when you do big P E3, so what big P takes is the normal in the reference configuration, reference normal. And what it returns you is the traction. It's like the actual traction, but per unit reference area. Okay, whereas in case of sigma n, which is giving you a small t, so this is deformed normal, this is deformed normal, and this is also the true traction, and it is per unit undeformed area. So here both are, in the deformed configuration, both are deformed. So this is, therefore sigma is the, it's a Eulerian stress tensor in true sense. It's an Eulerian stress tensor. Let us see, what about second pk? What is it? So second pk is big S, right? Which is also equal to, can you recall the relationship between P and big S? So P was equal to big F into big S. So this implies second pk big S is F inverse, big F inverse into big P. Isn't it?
Sir,
So when you, yeah, tell me.
सर ये स्मॉल टी है, ट्रू ट्रैक्शन पर यूनिट अनडिफॉर्म्ड एरिया की जगह पर यूनिट डिफॉर्म्ड एरिया होना चाहिए ना?
Right, right. Deformed area. Sorry. Okay. Or we can also say it's like, instead of true traction, I should say it's the actual force. Isn't it? It's the actual force per unit deformed area. And whereas this big T is actual force per unit reference area. So whatever the force is being felt by the body when you cut it, it's that force per unit reference area, that is big T. Whereas that force per unit deformed area, that is small t. Okay, but let us see what you get when you do big S into big N. So big S is this thing, so big S into big N, what is that then? So that's big F inverse into big P into big N, right? Which is big F inverse into big T. Now that doesn't look like, so this is obviously not the true force per unit reference area. So this is not. So what is it? If you also try to do it in the following way, so let us see what is big S into big N into d omega naught. So that's equal to big F inverse into big P into big N into d omega naught, which is same as big F inverse into that small force d big F, isn't it? Which is the true force. This is the actual force. So this implies big S into big N is F inverse into d big F by d omega naught. So what you see is that finally big S into big N is big F inverse into true force per unit reference area. So it is sort of, you have to pre-multiply by big F inverse. So, in many books you will see they also call it, when it is big F inverse, it is called pullback, pulling back to the reference configuration. Whereas if you pre-multiply by big F, then we say it is push forward. So it is, so this whole thing is a quantity which is true force per unit reference area being pulled back to the reference configuration. So it is simply a pulled back quantity. It is not a force which is acting in the reference configuration. Remember, it is just a quantity which has been pulled back. You remember that you have this reference and deformed, and it gets deformed. So any line element here, d capital X, that goes to d small x, and d small x is equal to big F into d capital X. So what is big F doing? Big F is pushing forward this d capital X to d small x. So it goes, when you go this way, it is push forward. Whereas if you go this way, it is pull back. So pullback is done through big F inverse, whereas push forward is done through big F. Okay, so that's sort of meaning of the second pK. And likewise, you can also think of what is the meaning of Biot stress. All right, any question? And then why do we have so many measures? It's just that, in nonlinear elasticity, you have so many strain measures. You have Green-Lagrange strain tensor, then you have deformation gradient itself, then you have right Cauchy green tensor, big C. So, and then you also have that big U, F equal to R. So these are all kinematic quantities, and we want to know what is the corresponding, thermodynamic conjugate of these kinematic quantities. So to get that, we did it in the last class. No, we said W dot. Let us find out W dot. So when we did that, we found out the corresponding stress measures. So you have so many strain measures in nonlinear elasticity, and corresponding to them, you have these stress measures. Okay.
Okay, sir.
All right. So we are talking about. Yeah. Please go ahead.
During our UG level, we defined like engineering stress as force per unit reference area. But we were writing all the like all the tensor form or matrix form as the Cauchy stress tensor only, but we were defining the stress as engineering stress or conventional stress.
Yeah, I must say that, in our UG course, first of all, we had only one stress, isn't it? Just Cauchy stress tensor. But we did talk about
Yes, sir.
engineering stress and I guess nominal stress or something, or maybe nominal stress is the engineering stress. We did have
True
stress.
stress and engineering stress.
True stress is the engineering stress. Okay.
No,
So
sir.
we had
True stress and engineering stress. For undeformed area, we called it engineering or conventional stress, or for deformed area, we called it true stress.
all right. So we had so first you can see that what we were calling stress in UG is actually traction, because you were always thinking of taking a beam, cut a section, find out what is the force, divide by the area, and we used to call it stress. But that is actually traction. It's just a stress component. It's not stress itself. Stress is a second order tensor. Okay? And in UG, so we only talked of referential traction and the the true traction, the Cauchy traction. When you divide force by actual area, then you get true traction. When you divide force by, sorry, when you divide force by current area, you get true traction. When you divide force by actual, the undeformed area, then you get um, engineering traction, I guess. Yeah, or they also call it nominal traction. But we never talked of the stress tensor. We always worked with the same Cauchy stress tensor. Okay, we had nothing like first Viola-Kirchhoff, isn't it, in UG class?
Yes, sir.
Any more comment?
Excuse me, sir.
Yes.
Uh, Sir, so we cannot find sigma, the current stress in the body, without doing the experiment.
Yeah, I mean, if you want to measure it, so you will have a deformed body, and the moment you cut it, then of course the stress gets relieved. But there is also something like photoelasticity. Have you guys done this experiment on photoelasticity in your UG course? I had done it.
Like we heard about it. Like we use
Yeah. So I had done it and I have also forgotten what it was. But using photoelasticity, I remember they could find out what is the stress in the body, the Cauchy stress in the body, the true stress. Now I don't know what exactly goes behind it, so I'll have to relook at it, or we will have to relook at it. But there is a way to find out the stress distribution in the body without cutting it. That is through photoelasticity.
Sir, but for sigma, like we require F first, no?
Say again, you require?
F, deformation gradient.
Well, so that is another way. So once, but for that, you also need the energy model, no? You have deformation gradient, then if you know the energy model, take the derivative of the energy with respect to deformation gradient, then you get the stress measure. But in actual experiment, you don't know what is the energy model. See, all these energy models, for example, the Vennat-Kirchhoff energy model, these are all approximations of the actual material behavior. Actual behavior is very complex. The Vennat-Kirchhoff model is just a data fitting of the actual behavior.
Sir, you said there are so many kinematic quantities, like the strain tensors are numerous, and for each strain tensor, we need a stress tensor, a thermodynamic conjugate. So, sir, we till now we have only seen the green Lagrange strain tensor in its linearized form.
Yes. Well, what I meant is not just strain tensor, but some kinematic measure of deformation. So this deformation gradient, big F, is also a kinematic measure of deformation. Big C is also a kinematic measure of deformation. Big U is also a kinematic measure of deformation. And likewise, big E is also a kinematic measure of deformation. So corresponding to all of them, when you find out their thermodynamic conjugate, then you get the corresponding stresses.
Okay, sir. So, sir, stretch is also a kinematic measure of deformation, like stretch.
Yes, 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 yes. Of course. So as you know, this big C, the stretch square, do you remember that stretch is lambda square in a direction big M is big C M dot M. So this stretch is directly coming from big C. And if you ask what is the what is the thermodynamic conjugate of this lambda, then I guess it must be related to the del phi by del C quantity, which perhaps is 2 times S, I guess.
So I think half
Del,
times.
del phi by del E is S, right? So
Yes.
del phi by del E is half of S or 2 times S?
I think half of S, because S was 2 times del phi by del C.
If it is half of S, then so it is related to half of S, this lambda square. Okay?
How did you relate?
Because you see here, this lambda square is coming from C, isn't it? It's a component of C.
Yes, sir.
So, and we know the derivative of phi with respect to C is half of S.
Yes.
So, derivative of phi with respect to one of the component of C will be
Okay.
one of the components of S. And the
Okay.
component of C is nothing but lambda square.
Yes, sir. Okay.
The diagonal component is lambda square.
Okay,
Okay?
sir.
Yeah. Okay. Any more question?
Phi is a function of C, invariance.
Say again?
And so phi is a function of the invariance of C. If you have C.
Well, that happens when you talk of isotropic model. So
Right.
till now, when we found out the thermodynamic conjugates in the last class, we had not imposed geosymmetry. So you had big F, you had big U, you had big C, you had big E. They could hold for any material model. The material symmetry had not come into picture yet. So when you start saying that find function of invariance, then you are restricting yourself to just the isotropic model. And then, of course, you can also talk of what is the thermodynamic conjugate of, let's say, big IC. So that's also possible. So to do that, you can simply, for example, you have your W of big F is equal to some phi tilde of IC, 2C, 3C. So this implies del W over del F. So when you take the total time derivative, you get double contraction F dot is equal to del phi tilde over del IC into IC dot plus del phi tilde over del 2c into 2c dot plus del phi tilde over del 3c into 3c dot. And then you have to work out these dots in terms of big F, in terms of big F and big F dot. And then you could relate then how are these derivatives related to the first pk, for example. But this will only hold for isotropic material. Okay.
Sir, for transversely isotropic, we got two more invariants. So in these terms, we will have two more additions, right?
Exactly. Yeah. Yeah. If you want to talk of transversely isotropic, then yes.
Sir,
Yeah.
sir, here like for getting the conjugates, we just take the time derivative of W
Yes.
with respect to F. The time derivative of W for various functions of W, like W of F we will
Yes.
take, and then we will
Correct.
equate it to something else. So then how do we conclude that these are the conjugates?
Okay, because okay, that's a good question. You see the energy. So we are basically, going by the spring model. In spring, for example, what is energy? Half of kx square, right?
Yes,
Which
sir.
is like half of kx into x, and kx is force, so half of force into x, where force is like a stress measure and x is like the strain measure. So you have to multiply stress and strain to get energy, and so the energy dot will be stress into strain dot. Okay, so therefore when you work out the dot, the quantity without the dot is the stress, and the quantity with dot, that's the strain.
Okay.
Yeah.
Sir, for vectors, like we have dot product, this double contraction is like that only, no? Like for tensors, we have double contraction instead of dot product.
Yeah, yeah, right. That's true. And why is, I think Devjit was asking why do we get double contraction? It is very simple. You see, this W is a function of big F, which will be changing with time. So when I want W dot, what do I have to do? I will do del W by del big Fij into d big Fij by dt from chain rule, which is same as Pij into F dot Ij. And there is a summation over both I and j. And this is nothing but P double contraction F dot, right?
So here is the thing that I had a confusion. Like what we are doing is whenever we are getting terms like Aij, Bij, we are writing it as double contraction A double contraction B like this. Uh,
Yes.
that is the general trend we are following. But when I was trying to see a few like videos or on YouTube and something, they are talking about the superscript and subscript and contravariant tensors, like all of these things in while trying to explain double contraction. So I couldn't relate exactly how what we are doing and
Right. Okay. Okay. Very good. You see, so what you went through was a more general treatment where they are also talking of curvilinear coordinate system. So you can remember, can you recall that we were also very briefly we talked about curvilinear coordinate system and why and how we have to use superscript and subscript, and the
yes, sir.
sum only when one of them is superscript and other one is subscript. So but we forgot about those things because that could have brought more complication. But for a general treatment, where you also want to bring in curvilinear coordinate system in that general treatment of the subject, then you have to start having superscripts and subscripts also. So right now we are just having subscripts, but when you have a general treatment, we need both. And that's how the subject has been developed, and you just saw that.
Okay, sir.
Yeah.
Sir, when we say that we are finding the constitutive relation, are we
Yeah.
talking about the W, the finding the energy function?
Well, so you see, often constitutive relation, by the way, is not just for elastic material. It can also be for viscoelastic or plastic, elastoplastic material. So, to be more general, when we say we want to get constitutive relation, that means we want to get relationship between stress measure and strain measure. And
Okay.
for elastic material or for hypoelastic material, it turns out you can define an energy. So only for hypoelastic material, the knowledge of constitutive relation is same as getting that W. Because from W you take the derivative and you can get stress, right? But for other material like viscoelastic or elastoplastic, no W exists. So that you take its derivative and you get the stress. There is no such W.
Okay.
Yeah.
And sir, by defining W as a function of the invariants,
Yeah.
are we taking into consideration the microstructure of the uh, element or the material?
Yeah, sort of, yes, certainly. For example, if it's an isotropic material, we say it is just IC2C, 3C. So what we are saying is that at the microstructurally, the body is such that it is same in all directions. So when you have random arrangement of crystal in the body, you see the same thing in all the directions. But and likewise, even for when you have a fluid body, it turns out for fluid body, the invariant is simply the determinant of F. So there you can do any deformation such that determinant of F is preserved. And all this is coming from the microstructure of the material, of course. So that's a very good comment, that material symmetry is guided by the microstructure of the body. Okay. Any more question?
Sir, when we have this symmetry, so like
Yeah.
Cijkl will not change.
Cijkl will not change. Okay, so I think so. You must have I think you are reading somewhere how to obtain this isotropic fourth order tensor. So yeah, that's what they do. So let me touch that part also since you have brought it up. So in linear elasticity, we say that sigma ij is equal toCijkl epsilon kl. And sigma is a stress tensor. I mean the components of a stress tensor, right? Components. And this is also the component of a stress tensor. So if you write this in a tensor form, it is basically the stress sigma equal to this fourth order tensor C multiplied with the second order tensor strain epsilon. Okay. Now, because this is a tensor equation, you can write it in any coordinate system, right? And suppose I write it in the E1, E2, E3 coordinate system. Then for sigma, you get sigma ij, and for C, you will get Cij KL. And for epsilon, you get epsilon KL. So this is in IJK coordinate system. Well, let's say it's E1, E2, E3 coordinate system. Whereas if I want to work out the same, write the same equation in E1 hat, E2 hat, E3 hat coordinate system, then sigma will be sigma hat ij, okay, and C will be C hat ij KL, and epsilon will be epsilon hat KL. All right. Now, because it's an if it's an isotropic body, even though these two are in different coordinate system, what it just means is that C hat ijkl should be equal to Cijkl. So for any two coordinate system, the C and C hats must be the same. Okay, but then because C is a fourth order tensor and we know how fourth order tensors transform, isn't it? So for example, this C hat ijkl could be equal to QIP QJQ QKR QLS into CPQRS. Do you remember the transformation of stress? Transformation of tensor. For a tensor, the components must transform this way if it has to remain coordinate free. So you now plug it in here, and what you get is QIP QJQ QKR QLS CPQRS is equal to Cijkl. Okay, so this is the restriction for C to be an isotropic tensor. So this has to hold for all Q in SO3 for all rotations. And when you work this out, using, so you can pick a specific forms of rotations. For example, rotation about E3 axis, rotation about E1 axis, rotation about E2 axis, and some more axes. So when you work it out, then you automatically find out what are the things which are 0 in the Cijkl number and which are non-zero, and it automatically gives you that it has only two independent constants. It must have just two independent constants. Okay, and there is a proof of also of this in some book. You can find it, I think, if you search on internet, you will certainly find the proof. And I know one of the books where you can find it, that's where we had read it. It's in YC Fung. I think it's Continuum Mechanics by YC Fung. Also available on internet, I think. Or maybe first course in continuum mechanics. It's something like that. First course in continuum mechanics. So in this book, you will find how using this relationship, they derive the fourth order isotropic tensor. So it's a very nice exercise to go through. You must see the proof.
So how do we get that C hat is equal to C?
Please say again. Oh, how did you get this?
C hat is equal to C.
This is from that experiment. You remember? I was because the can you recall that I had this experiment where if I was applying strain in this direction, let us say this is 1 and this is 2, and let us say I apply epsilon 1 1, and I measure sigma 1 1 and sigma 2 2. Okay, and in the second experiment I apply epsilon 2 2, and then I measure sigma 1 1, sigma 2 2, and sigma 3 3, let's say, and here also I measure sigma 1 1 2 2 3 3, and if epsilon 1 1 is equal to epsilon 2 2, what can you say about sigma 1 1 in the first experiment? Let us say 1 1 1 superscript for first experiment, and here it is 2. So what can you say about sigma 1 1 1 and sigma 2 2 2? What will they be? Will they be same or they will be different? If it's an isotropic material,
This would be same.
this will be same, right? So they will be same if it is isotropic. And likewise, what can you say about let us say sigma 2 to 1 and sigma 1 1 2? So it will turn out to be the same. Okay, and then sigma 3 3 1 will be same as sigma 3 3 2 because of the isotropy nature. Is that okay with you, Pulkit, and others also?
Yes, sir. But like I have one question.
Just a second,
The
so I'll also get there. But then from here, you will say that sigma ij is equal to Cij KL epsilon KL. Okay, and suppose here I choose a coordinate system such that now it is it's a red coordinate system having this is 2 and this is 1. Okay, so and let us say this is hat coordinates and this is hat. So here you will have sigma 1 1 hat, which is same as sigma 2 2 2 that I wrote here, isn't it? But this is equal to sigma 1 1 1 from the first experiment, and sigma 1 1 1, what is it equal to? Sigma 1 1 1 is C11 KL epsilon KL, which is also equal to sigma 1 1 hat. Sorry, this is equal to, sorry, this is not, yeah, right. This is equal to sigma 1 1 hat, but this has to be equal to C hat 1 1 KL epsilon KL. Okay, but in this experiment you are only applying epsilon 1 1 or epsilon 2 2, so this will become C 1 1 1 1 epsilon 1 1 because rest all are 0, whereas from here this will become equal to C hat 1 1 1 1 epsilon 1 1 because epsilon 2 2 So I should also say hat here. Epsilon hat 11, because epsilon 22 is same as epsilon 11 hat here, isn't it? So epsilon 22 is same as epsilon 11 hat. Okay. And when you compare these two, and as we had said, epsilon 11 hat is same as epsilon 11. This tells us that C hat 1111 is equal to C 1111. Can you see why therefore the hats are the same?
Okay, sir. So here in this image, where you applied the epsilon 11 and epsilon 22.
Yeah.
So where you apply it, basically you apply it on a like a point, a small particle at around a point, or where you are applying it,
Yeah,
and how
that's a
it
good question. First of all, we
maps
can't
to.
apply that point. We are just suppose that we are applying a deformation to the body such that at a point you just have epsilon 11 in the first case. And in the second case, you are applying a deformation to the body such that you just have epsilon 22 at a point. You can have epsilons at other places also in the body, but we are just concentrated at a point. So apply a deformation such that in the first case you have only epsilon 11, and in the second case you have only epsilon 22, and both are same also. Epsilon 11 is equal to epsilon 22.
So the point is also the same, means it is given by deformation map.
Point is also the same because we must concentrate on the same point, isn't it? Because isotropy,
Yes, sir.
this it is from point to point, no? So we have to
Yes, sir.
the same point also. We can't compare theCijkl of one point toCijkl of the other point becauseCijkl changes from point to point.
Sir, what you will do if the point will go on a surface?
Yeah, that's a good question. So basically, you can just so there, of course, you cannot apply all the strain measures there. So therefore, we have to do this experiment with a point which is inside the body.
Okay, and it deforms also to inside the body.
Yeah, so you have to apply a deformation. Just now we don't know what exact deformation we'll apply, but that is not the point also here. Just think of applying a deformation such that in the first case you just have epsilon 11 at a point, whereas in the second case you only have epsilon 22 at the same point. Now what deformation it will be, that we are not bothered about. We just want that somehow you have epsilon 11 at a point, and in the second case you have epsilon 22 at the same point.
Okay, sir.
Yeah. All right. Any more question?
Sir, I have a question that, sir,
Yeah.
in solid mechanics, anywhere means like anytime or we have used the chemistry of the chemical property of the material.
Okay.
I mean,
Yeah,
so
that,
we are talking about the microstructure only
yeah.
and not talking about the chemical nature of the material. So, did we any history or in the history also
Yeah, yeah.
have you have you used chemical property of the material?
See, we definitely look at the physics. For example, when you discuss crystalline materials, there is this concept of multi-scale modeling, which in fact I'm also going to teach in the next semester. So in that multi-scale modeling, we try to obtain the property of a material from the molecular structure of the material. So we look at the physics. We don't look at the chemical bonds or the reactions that are taking place. We just look at the physics of how the forces are acting between the atoms. And that is used to obtain the material property. I guess chemistry can also be useful somehow, but I can't think of it. Certainly when you have a multi-physics problem where there are things like you are deforming the body and it excites reaction within the body, so then you have to also talk about chemical property of the body, and then the chemistry and mechanics both gets coupled also.
So
It
till
happens
now, nobody has
biological.
done this. I mean,
Some people must have done it, but not in the general. I don't think anybody has done it in a general framework, and I think the general treatment is also not so easy because it's so complicated. And this often happens when modeling biological system where you have physics, chemistry, and mechanics, everything there. Okay, so I'm sorry I can't give a very good answer to all these because these are tough questions, and I haven't thought about it so nicely before. But the treatment is possible, of course.
Yes, sir, actually, in undergraduate studies, we take books like James Gary or Baron Johnson.
Yeah.
Sir, are these books really helpful for teaching? Should we actually start reading our solid mechanics from these books, or we should directly go to the mathematical theory? Because somehow we feel that as we go ahead into our master's and PhD courses, the theories that are given in those books do not suffice us, and somehow the theories are not correct. Is it like that we should simply, yes, is it like we should start with some mathematical theories of solid mechanics and start from there? If that is the case, then which book should we start with?
See, first of all, in UG level, you cannot talk about these theories because they are so complicated for a UG student. And not just this, even the topics that are covered in UG, they bring physical insight into solid mechanics. You see, these things are quite mathematical. If you start directly with this, a student won't be able to appreciate the physics behind it. See, you guys are matured, you have done undergraduate, so you have already some understanding of the physics, and therefore you can take this course. But a first year or a second year undergraduate student cannot take this course directly. So therefore, those courses are also relevant. Okay, and only when you have taken these courses that you can then start this course. You cannot skip that course. So I hope I answered your question.